In the quiet darkness of space, a colossal force field wraps our planet like an invisible cloak. For billions of years it has guided migrating birds, protected our atmosphere from the relentless solar wind, and powered the compass that steered ancient explorers across uncharted seas. Yet recent measurements reveal a troubling truth: the strength of Earth's magnetic shield is steadily declining, and the very poles that have anchored it for eons are beginning to wander. This is the story of a planetary guardian in retreat. The magnetic field originates deep within the planet, in the molten iron outer core that churns beneath the solid mantle. As the liquid metal circulates, it generates electric currents, and through the dynamo effect, these currents produce magnetic fields that coalesce into a dipole aligned roughly with the planet's rotation axis. This geodynamo is a delicate balance of heat flow, rotation speed, and compositional changes, a natural furnace that has kept Earth alive since its fiery birth. Scientists first noticed the field's weakening in the late 20th century, when satellite data from missions such as Arsted and CHAMP showed a global drop of about 5% per century. Ground observatories echoed the trend, recording a steady decline in magnetic intensity over the continents. The most striking evidence came from the South Atlantic anomaly, a region where the field is markedly weaker, allowing radiation belts to dip closer to the surface and endanger satellites and high-altitude aircraft. Historical records extend our view far beyond modern instrumentation. Paleomagnetism, the study of magnetic minerals locked in ancient rocks, reveals that Earth's field has flipped polarity dozens of times, with the last reversal, the Bruns Machiyama, occurring roughly 780,000 years ago. These reversals are not instantaneous, they unfold over thousands of years, during which the field weakens, becomes multipolar, and the magnetic poles wander dramatically across the globe. Why is the field weakening now, after a period of relative stability? One hypothesis points to a slowdown in the heat exchange between the core and the mantle. As the mantle cools, it can alter the pattern of convection currents, diminishing the efficiency of the dynamo. Another line of research suggests that the growth of a solid inner core, which began about 1 billion years ago, changes the geometry of fluid flow, subtly reshaping the magnetic field's architecture. Computer simulations provide a window into these hidden processes. By feeding data on temperature, composition, and rotation into supercomputers, researchers can recreate the swirling iron currents that generate the field. Recent models have reproduced the observed weakening and the drift of the magnetic North Pole toward Siberia at a rate of roughly 55 km per year, a speed unprecedented in the past 2 centuries of measurements. The movement of the magnetic North Pole is not merely a cartographic curiosity. Navigation systems that rely on magnetic bearings, aviation, maritime, and even smartphones, must constantly update their reference models. As the pole shifts, the World Magnetic Model, a standard used by the U.S. Department of Defense, has been revised more frequently, highlighting the practical implications of a wandering field for modern technology. Beyond navigation, the weakening field could have profound effects on Earth's atmosphere. The magnetosphere deflects charged particles from the solar wind, a thinner shield allows more of these particles to erode the upper atmosphere. Over geological timescales, this could accelerate the loss of volatile gases, altering climate patterns and even affecting the habitability of the planet. The danger is not hypothetical. During the last magnetic reversal, evidence from ice cores and sediment layers suggests increased radiation reaching the surface, coinciding with higher mutation rates in biological organisms. While life survived, the period was marked by ecological stress, hinting at the possible challenges humanity might face should a rapid decline in field strength precede a reversal. Yet not all scientists agree that a reversal is imminent. Some argue that the current weakening is part of a long-term cyclic pattern, comparable to the 1,000-year oscillations observed in the Holocene epoch, which did not culminate in a full polarity flip. Others point to the resilience of the dynamo, noting that even during past low field intervals, the field never vanished completely. To resolve these debates, an international network of observatories is expanding. The Swarm mission, a trio of satellites launched by the European Space Agency, now measures the magnetic field with unprecedented precision, mapping tiny variations over the planet's surface. Complementary ground stations in remote locations, from Antarctica to the Sahara, feed continuous data into global models, sharpening our forecast of the field's future trajectory. Public interest in the magnetic field has surged, spurred by headlines proclaiming the end of the world. While sensationalism exaggerates the timeline, reversals unfold over millennia, the reality remains that a weakened shield could increase exposure to solar storms. The 1859 Carrington event, a massive solar flare, caused telegraph systems to fail worldwide. A similar storm today could cripple power grids, satellite communications, and GPS networks. Mitigation strategies are already under discussion. Engineers are exploring hardened satellite designs, more robust grid architectures, and early warning systems that detect solar eruptions minutes before they strike Earth. Meanwhile, policymakers are urged to incorporate space weather considerations into infrastructure planning, ensuring that society remains resilient in the face of a potentially more volatile magnetic environment. The story of Earth's magnetic field is a reminder of the planet's dynamic nature. From the fiery furnace at its core to the shimmering auroras at its poles, the field connects deep geological processes with the fragile tapestry of life on the surface. As we watch the magnetic north inch across the Arctic tundra, we are witnessing a slow, inexorable change, a natural phenomenon that challenges our technological dependence and invites deeper respect for the forces that sustain our world. In the end, the magnetic field's decline is not a catastrophe awaiting us, but a call to understand the planet we call home. By deciphering the language of molten iron and magnetic lines, we gain insight into Earth's past, safeguard its present, and prepare for a future where the shield may dim, yet humanity's curiosity and ingenuity shine brighter than ever. Beyond the polar lights, the weakening field subtly reshapes the behavior of migratory species. Birds, sea turtles, and even whales rely on geomagnetic cues to navigate vast distances. As the field drifts, their internal compasses falter, leading to altered routes and unexpected stopovers that ripple through ecosystems. In the realm of technology, the magnetic shield safeguards the delicate dance of satellites. A softer field allows increased exposure to charged particles, which can degrade solar panels, corrupt onboard electronics, and shorten mission lifespans, prompting engineers to redesign shielding and orbit strategies. On the ground, a diminished magnetosphere amplifies the reach of solar storms, threatening power grids. The 1859 Carrington event serves as a cautionary tale. Modern grids, far more interconnected, could experience cascading failures without robust geomagnetic mitigation. Yet humanity's response is already unfolding. International collaborations are deploying a new generation of magnetometers, launching CubeSats to map field fluctuations in real time, and integrating AI to forecast geomagnetic hazards, turning vulnerability into a catalyst for scientific unity.